Hello, my name is Felix Weber and today I am going to present you the concept of Real AI Gym, an affordable and open source research platform for dynamic robot control, which is currently developed by the underactuated lab of the DFK RIC in Bremen, Germany. In the style of the popular OpenAI Gym, which provides a benchmarking environment for reinforcement learning algorithms, we named this project Real AI Gym, which stands for Real Athletic Intelligence Gym. In contrast to the OpenAI Gym, the idea of Real AI Gym is to generate dynamic robotic behaviors not just in simulation, but also on real hardware. Many modern robots are inspired by animals or humans, and researchers aim to reproduce their agility. An inherent feature of these robots is that they are underactuated, which means for designing dynamic and compliant behaviors which are robust to contacts with surroundings, the robot's system dynamics have to be taken into account. In today's robotics research landscape, it is common that research groups only have access to one or a few real robots. Consequently, many control methods are developed and tested only for the few robots which are available in the group. Seldomly different control methods are directly compared on the same real robot, or a single control method is methodically benchmarked on a variety of systems. Often it is impossible to reproduce results from other research teams. Real AI Gym tries to overcome these problems by providing a set of canonical robotic hardware setups together with openly available software and tested controllers. The philosophy of Real AI Gym considers the following key points. Many commercial systems are expensive and some additionally require software licenses. Real AI Gym provides instructions for building low-cost hardware and freely available software. The platform should be easily accessible for users and contributors. Due to its wide distribution, Real AI Gym utilizes Python 3 as the main programming language, which allows for quick prototyping, testing, and easy onboarding of new members. Real AI Gym tries to achieve reproducible results with standardized hardware and open and thoroughly documented software. The transparency of open source software is the basis for reproducibility and Real AI Gym's usage in educational contexts. Real AI Gym has state-of-the-art controllers from control theory and reinforcement learning built in, which show the capabilities of the canonical robotic systems and provide examples for the software interfaces. Real AI Gym makes it possible to quantitatively compare controllers and assess their advantages and disadvantages in different settings. With a low entry barrier, detailed documentation, and freely available software, Real AI Gym is designed to be used in education and help students and newcomers in the field to overcome the gap from simulation to real robot hardware. Dynamic motions, as Real AI Gym aims to realize, require high bandwidth torque control. For this, Real AI Gym utilizes quasi-direct drives from CubeMass and MJBots, which feature a high mechanical transparency with open source firmware and CAN communication drivers. A single one of these motors can be operated with approximately 1.5 kHz in Python 3. Real AI Gym accommodates standard control systems which are inspired by humans and animals. On one hand, the canonical robots in Real AI Gym should be simple in order to be reproducible and accessible. On the other hand, the complexity of the control problems that they offer should be non-trivial. These here are the systems that are currently in operation in the Real AI Gym. Control problems of these systems include generating motions for swing-ups, hopping, backflips, and brachiation. The first system is a torque-limited simple pendulum, which is arguably the simplest underactuated robotic system one could imagine, with only one motor, a link, and a weight, and can be reproduced easily. A natural control problem for the pendulum is to swing up and stabilize it on top with a torque limitation. A double pendulum is a standard 2 degree of freedom control system with chaotic dynamics. By disabling one of the motors and using it as a passive joint, the system can be operated either as an acrobot or as a pendubot. Similar to the simple pendulum, a natural control problem is to swing up the double pendulum and stabilize it in the top position. The hopping leg is a 3 degree of freedom system with 2 motors and 1 passive vertical degree of freedom. The leg is able to jump by pushing itself off from the ground. Interesting control problems are maintaining a constant jumping height and performing a backflip during the aerial phase. An acromonk consists of 2 links which are joined together by a single motor. 2 hooks at the external ends of both links facilitate the acromonk to hold onto horizontal bars. As a free and wireless system, the acromonk is capable of performing brachiation behaviors similar to primates. The Simple Pendulum platform is already released on GitHub, including a documentation page. There are detailed instructions for building the hardware. A CAD model has been uploaded to grabcad.com for online viewing. A variety of controllers has been implemented and documented. First benchmarking results are also already available. This brings me to the outlook. The open source releases for the Double Pendulum and Acromonk, as well as taking a broomstick hopper into operation, are planned for the near future. For all systems, it is envisioned to have leaderboards based on benchmarking criteria to motivate students and researchers to participate in the project and establish a baseline for different control methods. With more available systems, we intend to introduce RealAI Gym to a wider audience. Thank you for your attention.